Thank you. Let us now take an example of a slightly more complicated example of a PLA. So we have to produce 6 functions, Z1, So this is an example of a little bit more complicated PLA than whatever I discussed in the last class. So there you see in this case there are 5 input variables, 5 input variables, A, B, C, D, E, okay? A, B, C, D, and E. And complements of some of them. May not be that I have used the complements of all of them, but some of them are complements of some of them are there. Then there are 6 outputs. Z1, Z2, Z3. And 8, you can critically examine, you will find that there are 8 products. And they are A bar, E bar, A bar, B bar, C, A, B bar, A, B, C, D bar, C, E, C bar, D, and D. 1, 2, 3, 4, 5, 6, 7, 8. Is it all right? So you can see that you can define a PLA in general by quantifying the number of inputs, the number of outputs, and the number of independent productors. The number of independent productors. And normally such a PLA is normally called a 5 by 8 by 6 PLA. Such a PLA is normally called a 5 by 8 by 6 PLA, or in general we call it a V by P by Z. V represents variables, V represents variables, P represents products, and Z represents output. Alright? So V represents variables, 5 variables are there, inputs. P represents products, 8 independent products are there. And Z represents outputs, 6 such outputs are there. So this is an example of a 5 by 8 by 6 PLA. Now try yourself the PLA realization. Now for PLA realization, I will just ask you to do the following. I will do it myself, but you can also try yourself. What I will be doing is, you have seen that in a particular row in AND plane, you remember, how do I show the transistor? You remember this is a particular column. In the AND plane, this is a row and this is a column. And how do I connect the transistor? Like this. Am I correct? And instead of repeatedly drawing the transistor, I will dot this particular node. That means I will draw it simply like this. Instead of drawing the transistor repeatedly, so at whatever location there is a transistor to be connected, I simply put a dot here. This is called programming the PLA, dotting the PLA. Sometimes we call it in the language of PLA called dotting the PLA. Similarly, in the OR plane, you remember we have a row like this, but this row now is the input. In the OR plane, this row is the input, and this is the output. And you remember that I am connecting my transistors like this. Okay? Instead of repeatedly drawing the transistor like this, I will show it by this configuration. So draw the load transistors as indicated in the earlier case. I am not interested in this because I know that the stick diagram is just for for showing you the reality of connection in actual VLSI layout. But I am interested that to draw the PLA in the normal kind of format which I have used earlier, that is this kind of thing. Only thing is here, instead of drawing the transistor, I will put a dot, etc. Similarly here I will show you a cross, a square in these two locations, here and here. At this location one square, at this location and square, and so on and so forth. You do it yourself now. You implement the function which I have just now drawn. I have just now given you in PLA form. This function has to be shown in PLA form. You try it independently. I am drawing it here, but you try it independently. Don't look at here in my diagram. You do it independently. Afterward, you look at me. Whatever there in the television, you look at that afterwards. Okay, is it over? So this is the, that this is the basic structure you have to draw first. This is the AND plane and this is the OR plane. Then you have to dot them suitably. Simply dot, or that called program them suitably. To produce A bar, what you have to do? Simply so here you have to put a dot. To produce, maybe you are not, this is not properly visible, but still you know the terms. A, this is A bar, A B bar, A bar B bar C, A B C D bar, C E, C bar D, D E and E bar, whatever way I have drawn. Then A B bar, how to produce? You have to have A bar at the input, so here, and B at the input. To produce A bar B bar C, I have to have A at the input, B at the input, and C bar at the input. To produce A, B, C, D bar, I have to apply A bar at the input, B bar at the input, C bar at the input, and D at the input. To produce C, I have to apply C bar at the input and E bar at the input. To produce C bar D, I have to apply C at the input and D bar at the input. D, D bar at the input and E bar at the input. E bar, simply E at the input. So the product terms are generated. Now I have to combine them. You can look at the functions. So for example, I want to produce Z1, which is the OR of DE and E bar. DE and E bar. So what is DE line? DE line is this one. So I have to put a square here. And E bar is this one. So Z1 is produced. Z2 is C and C bar D. CE and C bar D. C is this line. The other is C bar D. C bar D is this one. Z3 C, C bar D, E bar. Z3 C, C bar D, E bar. Z4 is ABCD bar, A bar, B bar, C. ABCD bar means this one, and A bar, B bar, C is this one. Z5 is A and A plus AB bar. Z5 is A plus B bar. A means this one, sorry, A bar and AB bar. So this one and this one. And finally, Z6 is A bar, B bar, C and AB, C bar. Over. This is an example, of course, a regular PLA. And what is the kind of PLA it is? PLA which is 5 by 8 by 6, regular. Normally, in many textbooks you will find that the square kind of representing a transistor is not there. The concert textbooks, you will find only the dots are there. They put simply dots here instead of showing square. Is there any mistake? You know that actual fact is these two are identical. It simply is the rows and columns interchange. Please, but one has to keep in mind that here dot indicates the gate is connected to these rows and no, the drain is connected to the rows and gates are connected to the columns. And if I put a dot here, the second dot will assume that the gates are connected to the rows and drains are connected to the columns. Please remember. But I prefer to use this square because we are drawing it in the same plane, the same, the same fashion, same route. Therefore, I prefer to use this kind of thing. But I have seen that many textbooks, they do not follow that. They follow a thing. Just instead of drawing it like this, they put another. But these dots, you have to keep in mind the transistor is actually connected like this. So don't get confused. In some other fashion, what they do, people, normally they draw this thing again below it. The AND plane is drawn above and OR plane is drawn below, and the columns are again made in the rows and columns represent the same thing. That means all these things are as if rotated by 90 degrees. All rows are as if rotated by 90 degrees. Then it becomes so-called input lines, and then all the columns are rotated by 90 degree in the inverse direction, anti-clockwise direction, they become outputs. So in that case, dots, there is no problem in showing the dots. But it is preferable to use this kind of thing. It is more convenient, I'm sure. But this kind of regular PLA, as you will easily understand that you just see that how many transistors are really being utilized. You just see. Can you count the transistor here? Transistor effective number of transistors which have been utilized in both AND plane and OR plane. So total number of transistors utilized are naturally these are there, they're common. Similarly, inverter, 2 transistors in each inverter, they are there. Okay, and only the transistors which are utilized is really a small, that really around 1/3. You can, by visualizing, I can say around 1/3 of the transistors available. They are all available, but I am not utilizing them. Similarly, in the columns of in the OR plane also, this picture is very similar. So naturally, these transistors are occupying unnecessary areas. This is not leading to a high packing density. Design is simple, but there are 2 bad aspects of it. One is that complexity is less, packing density is less, that means complexity is less. And secondly is, I have to use longer wire routes. And as a result, delays will be more, speed will be affected. So therefore, regular PLAs are very simple so far as design is concerned. So far as realization is concerned, it's very simple. Even you can take a project and you can do it yourself here in our laboratory. It's not a difficult task. But from implementation point of view, you'll find that we are unnecessarily sacrificing space, which is so valuable in VLSI technology today. And secondly, that thing is leading to some other things like more delays, etc. More delays, more power, standby power dissipation. There may be more standby power, all these problems are there. Therefore, people go for folding the PLAs. What is meant by the folding of PLAs? You see that, is it possible to reduce the number of rows? That means, can we split the rows? Instead of using, how many rows are there? 8, because 8 products are there, therefore there are 8 rows. Can we split the rows into 4 plus 4? That means I have got 4 rows this way, 4 rows the other way, and I put the OR planes on either side. Instead of using a single OR plane to the right of the AND plane, what I can think that I paint the AND plane at the center and 2 OR planes. I split the rows, and that's how we can make a compaction which is leading to better utilization of the transistors in the VLSI. This is called row folding. Similarly, it is also possible to fold the column. I can split the columns. I can do the folding of rows and columns not only in the AND planes but also in the OR planes. So there are four possibilities for compaction. One is the AND plane row folding. The other is AND plane column folding, by folding my splitting and putting so that properly the transistors are utilized. OR plane and row folding, and OR plane column folding. And if I can fold means that the way it is you are splitting the rows and columns appropriately, so that you are making a better utilization of the transistors, which ultimately leads to compaction and therefore higher speed, lower power dissipation, and everything. And that will be the aim now naturally, because regular PLA is very simple. Whatever complicated problem I can give you, you can do it immediately without any problem. It is very simple. That way is rather simple. But let us now, I think whatever remaining time is there today, I'll try to give an example of the row folding of the AND plane using the same example. Now, if you are interested in the row folding, you first organize these product variables, the products, in such a fashion that A, B, C, D, E, these are most separated from each other. I first consider whether there is A or not. I first see whether any term is there which involves A only. I keep its position in the beginning, in the first. Then I try to see that is there any term involving AB. Then sequentially A gets priority, A bar gets less priority, B gets priority, B bar gets less priority. That way I arrange the term, second and third term. That's way I go on proceeding to start whether there is a term ABC, BC. That means from A I give topmost priority to A, then A complement, then B, then B complement, and that's how I first arrange the product term. That is a very fast task. And that's how what I am doing here, if you see, I am arranging the product terms in this fashion, the same way I have arranged here earlier. A bar, A, B bar, A bar, B bar, C, A, B, C, D bar, C bar, D, C, E, D, E, and E. You just see the way I have used the same. I started with A, but there is no A. So there is one term is there which is A complement. So I have given the first topmost priority in location. Then I am trying to search out AB is there. Yeah, I have got only one term, that is A B bar, so I have given it second position. Then ABC, only term is this. But suppose there was some A B bar C, which one would have come first? That one would have come first, because A is there. Here A complement is single term, no problem. Then A B C D, only one term, no problem. Then I find that there is another term without involving AB, but CD is there. It gets a second priority. Then I am trying to find an A, B, C, D, E. Nobody is there, only C is there. A, B, C, D, one is, A, B, C, D, there are two terms. One is C, the other is D. And the third term is actually third term. A, B, C, D, there is A, B, C, A, B is missing here, C, then A, B, C is missing here, D, and A, B, C, D is missing here. That's how I have arranged them in the order of, that variables, starting giving topmost priority to A and worst priority to E or E bar. That's how I have set. Then what I do, I split the rows like this. I make first row like this. In one side, in the left side, I keep A bar. And in the second side, that means I divide into 4. I put the 8 outputs are divided into 4. So A bar and C bar D. second row, A bar, B bar, C, sorry, A, B bar and C. Third row, is A bar, B bar, C and D. And fourth row is A, B, C, D bar and E bar. What I really want to do in this particular case, that I want to produce the four functions A bar, A B bar, A B bar C and A B C D bar in the left hand plane, in the left side, and C bar D, C, D, E bar in the right side, and correspondingly I will put the OR planes on either side. Here you note, you can easily find out that, for example, Z2, you just check the example, Z2 is independent of Z2 is independent of AB. There is no AB here in Z2. Z3 is also independent of Z2 and Z3 is also independent of AB. Z2, Z3, that I can put this Z2, Z3 in the right hand plane. Similarly, oh yeah, Z1 is also, yeah, Z1 is also same thing. Z1 is also. Then what about Z4 and Z5? Z4 and Z5 and Z6. Z4, of course, this example has been, it's a tailor-made example, but it could be made very arbitrary. These three things are independent of more or less you can say that E and kind of thing. C is there. And accordingly, you shall see that we shall split the OR planes on two halves, locating Z1, Z2, Z3 in one side and Z4, Z5, Z6 the other side, as shown here. You can just try yourself. So this is a little bit more complicated, but you can understand it. I'm not trying to do any folding of the columns. Only the rows have been folded. It's like this now. Use of blackboard would have been more convenient for drawing. Anyway, just say that what I have done, as indicated here, the first row has been split into two. A bar being produced to the at the left and C bar D at the right. So what I've done, you see that I have broken. I have to break this row somewhere. I have broken it here. Anywhere between this node and this node, I could break it. The row has to be broken, isn't it? Anywhere between this node and this node naturally produces A bar. A is just inverted. Whereas this one has to produce C bar D means C at the input and D bar at the input. So there should be a load for that. There should be a load. This is a load transistor for this inverter, this NOR gate. But this is the load transistor for earlier case. What I did, the load transistors were all shown at the left. All the load transistors of the different inverters or NOR gates were shown at the left, but that I cannot do now because the left and right side will be utilized for producing the two OR planes, for realizing the two OR planes. So I have to split the transistor row somewhere and go vertically up or down, whatever convenient, and place my corresponding load transistors. So one thing I should have mentioned earlier, this is all the load transistor, whatever I have drawn so far, they have been shown to be depletion mode MOSFET. This is all nMOS technology. This PLAs so far discussed, they are all nMOS technology. The depletion mode loads have been used. Why? Because in that case, all the transistors in the N and OR plane, these are nothing but the transistors of either inverters or NOR gates. They should have a smaller W/L ratio, around 4:1 or 5:1. But if I had used nMOS technology, the other kind of configuration, each nMOS would have taken a lot of area. The overall chip area would have been very, very large. Therefore, HNMOS or HMOS technology is most suitable for nMOS kind of realization, where the load transistors are all, please remember, these are very important. Load transistors are all depletion mode MOSFETs. Okay? And this one is done. I think now it is understood that how I have realized the different variables. I have split here. Where the splitting has been done? Between this node and this node. Has to be done somewhere, anywhere. I have shown it. I could do it here. Splitting could be done anywhere. Similarly, here I have made the splitting between this one and this one. So at this point, there is no much space available. I have to do the splitting here. In this case, there was some better scope. You know that I could make the splitting any point from this node to this node. But here that scope is not there. Same thing for this particular thing. I have split the rows in such a way that they are separated and the corresponding independent NOR gates are available for producing either the inversion or the NOR functions. Then thereafter I have to put the OR plane suitably. You do it yourself. I think today time is over. Thank you.